Hello, everyone. Thank you for being here today. We are going to be presenting an update on the fluid serviceability and maintenance workstream for cold plate-based liquid cooling. My name is Sean Barlett. I'm a data center facilities chemical engineer with Meta. I am joined today by Dr. Philip Yu, who is a global senior industrial technical consultant with NALCO Water. The fluid serviceability and maintenance workstream is part of the OCP Cooling Environment's Advanced Cooling Solutions cold plate subproject. The focus of this workstream is to address the scalability challenges of deploying inhibited propylene glycol and treated water fluids in TCS loops with liquid-cooled racks using cold plates. In this session, we're going to be presenting an overview of two contributions from the community designed to support deployment of these technologies. Sorry about that. Within a data center facility, there will typically be two fluid circulating loops directly involved in cooling IT equipment with a CDU barrier in between them. On the facility water side, there will be a heat transfer fluid that carries heat from one side of the CDU and rejects it in some type of cooling system, such as a chiller. On the TCS side, where the IT equipment resides, a heat transfer fluid will carry heat from the cold plates connected to the IT equipment and reject to the CDU. The focus of this work stream will be the heat transfer fluid in the TCS loop. Based on feedback and discussions at last year's Open Compute Global Summit, the Fluid Serviceability and Maintenance Workstream was created within the Cooling Environment's Cold Plate Subproject. The goal was to bring together treated water and inhibited propylene glycol subject matter experts to address the needs and requirements of cold plate liquid cooling for data centers. While industry has a long history of expertise in larger traditional cooling systems, there's a limited amount of experience with direct-to-chip liquid cooling at scale. Other areas of concerns were to address the additive requirements and serviceability to start up and maintain these loops. The intent of this workstream is to address the needs of systems and operators of all sizes, with the overall goal of the workstream to enable a multi-vendor supply chain of cooling fluids to support the growth and scalability of direct-to-chip liquid cooling. There were two main fluids that were investigated as part of this workstream: water treated with chemicals and inhibited propylene glycol. Some of the most important considerations when looking at these two fluids are the physical and thermal properties. Treated water has better thermal properties, is less viscous and less dense. However, propylene glycol in concentrations over about 25% is bacterial static. Propylene glycol also has a lower freeze point. Both of these fluids are going to require some consideration to manage corrosion in the system, while treated water is also going to require consideration to manage biogrowth. The two white papers outline recommended properties and parameters for each of these fluids, though actual properties may differ due to specific system design and treatment programs. All of the properties and parameters have been selected to minimize corrosion in the system and biogrowth. The work stream at this point has assumed that no carbon steel will be in the system, and the systems will have a large copper surface area to water ratio due to the wetted surface area of the cold plates. The properties and parameters in these white papers can be used to aid in the selection of heat transfer fluids and additives. As these heat transfer fluids go through their life cycle, it's assumed that additional treatment chemicals will be required to meet the needs of the treatment plan. As these additional chemicals are added, it should be expected that the fluid properties will change. The workstream discussed different options for pre-mixed and on-site mixing fluids, though all of these properties and parameters should be discussed with system stakeholders to evaluate the pros and cons of each. The TCS loop is an integrated system with many different components, some of them what we've talked about today, such as pumps, piping, CDUs, cold plates, and quick connects. It's very important that system designers consider the compatibility of each of these materials with the heat transfer fluid. Each of the white papers contains a list of acceptable wetted materials, which are broken up into two categories: one list for metals and alloys, and one list for plastics, elastomers, and other materials. It's very important to note that neither of these lists are intended to be exclusionary in nature. The workstream team took a cautious approach due to the limited amount of available corrosion data for similar applications. Additional materials can be used, though evaluation is recommended. At a minimum, it's recommended that some type of lab scale testing is performed, though ideally, testing should be done at a system level with representative components such as CDUs and cold plates. Here is a brief summary of the awarded materials list for metals and alloys. It's primarily expected that these materials will be used for components such as CDUs, piping, connectors, and pumps. The recommendations on this list are primarily to limit corrosion in the system and capture concerns with plating wear during normal operation. Here is a summary of the elastomers, plastics, and other materials list. It's expected that these materials will be primarily used for components such as tubing, gaskets, and seals. The recommendations here are based on material compatibility and the temperature limitations of the system. The list between the two fluids is generally very similar, though there are certain exceptions with materials such as CPVC, which is not compatible with propylene glycol fluids. In terms of sampling and monitoring of the TCS loop, it's recommended that an operations and maintenance plan is developed to ensure that the system is meeting the treatment plan goals over the life of the fluid. The two white papers outline recommended testing parameters and procedures. It's expected that in the early life cycle of the fluid, testing frequency will be higher, but it can be decreased once the system reaches steady state. Those specific testing frequencies should be determined by key system stakeholders, taking into a number of factors such as specific system design, operational considerations, and failure tolerance. The minimum recommended testing frequency is annual testing. It's recommended that all testing results are shared with the fluid supplier, who can aid in the determination of additives and replacement of the fluid. Some of the takeaways that the Workstream team had. The TCS loop is a heavily integrated system with many different components and stakeholders. It's very important that everyone involved in the development of these systems coordinates their actions. The heat transfer fluid is just one of many components, though it's a component that generally touches all of the other ones. Throughout the life cycle and development of these systems, it's very important that the different stakeholders coordinate the materials, design, and operational parameters for the system. To use an old adage, a chain is only as strong as its weakest link. If one component in the system fails, it's likely that that failure will affect other components. Additional work was identified needing to standardize the qualification of new fluids and compatibility with different materials. I just want to take a minute to thank the other major contributors to the white paper who are not here with us today. If it was not for them, we would not be able to produce these two documents. And I'd like to make a call to action. While we did have a great team, it's always great to have more input from others. So if anyone is interested in either the ACS cold plate sub-project or the fluid serviceability and maintenance workstream, I encourage you to go to the Open Compute website and take a look at the schedules for these meetings and join. At this point, the two white papers have been released and are live on the Open Compute website. Those can be found by doing a search in the contributions section, and there's some additional information that can be found on the sub-project wiki. That's the presentation. If anyone has any questions.
Can you go back to the previous slide? Yeah, all the information on the white paper, you can look it up on the ACS cold plate subject project wiki. So you want a whole copy of the white paper, you can actually download it. All the wet material list and all the criteria for testing, sampling frequency is all listed there.